Hello dear friends, welcome to a lecture on ring theory. In this lecture we shall study special types of rings which are known as Euclidean rings. I have written here definition. We shall see the definition, then we shall see some examples of Euclidean ring, and then we will prove properties of Euclidean ring as theorem. So I have written definition here. An integral domain R is said to be Euclidean ring. So what is integral domain? That we have studied earlier, a commutative ring without zero divisors. That means a ring is commutative, R is commutative and without zero divisor. That is AB equal to 0 implies A is equal to 0 or B is equal to 0. These are the properties of integral domain, and this is Euclidean ring if for every non-zero element A not equal to 0 in R, means every non-zero element of the ring there is non-negative integer D of A. There is assigned a non-negative for every non-zero integer or every non-zero element of ring, we assign non-negative integer value to that element D and denote by D of A. Having these two properties, this D of A has, it is non-negative. Non-negative means either 0 or greater than or equal to 0, integer. It is integer and it satisfies these two properties. For all A, B belongs to R, both non-zero, D value of A is less than or equal to D value of AB. And second is, for any two element A and B in R, B is not equal to 0, there exists Q and R, another element in R, Q and R, pair of elements such that A is equal to QB plus R, and where either R is equal to 0 or D of R is less than D of B. Now see, the second is division algorithm. Second property is division algorithm from number theory, and here the integer A is divided by integer B in number theory we have, and let Q be the quotient and R be the remainder. Then here we have to subtract from A QB and R is the remainder, and the equation can be written as A is equal to quotient into divisor plus remainder. And what are the condition for the remainder? The remainder is either 0 or the remainder is less than B. So here instead of R less than B, the condition written as D value of R is less than D value of B. And so thus this is the definition of Euclidean ring. For Euclidean ring, it is integral domain and we assign for every non-zero element D value satisfying these two conditions, and we do not assign a value to 0, D value of 0. So now we shall consider some examples. Example of Euclidean ring. Example 1. See, first example we can consider the set of integers, ring of integers we shall say. The ring of integers is a Euclidean ring. Now we shall verify this, but we have to define D value, where D value of A is equal to absolute value of A. Or that means, see, this is for all A not equal to 0 in the ring. In the ring of integers, we shall denote it by I. Now the solution for this, we shall verify this is Euclidean ring, and it is easy to verify. See, we will denote the set of ring of set of integers by I, and that forms a ring. We have seen this as an example of ring. B, the ring of integers. And we have here D of A. for 0 not equal to a belongs to I, we have, or let us define, d value of a is equal to absolute value of a. Now we shall verify this satisfies these two properties. So let for first a be in R. Let a be in I. R means here integers. Two integers, both non-zero. A not equal to 0, b not equal to 0. We will verify that. So we have d value of a into b is equal to absolute value of ab, and that absolute value of ab can be written as by property of absolute value function mod a into mod b, and thus but this is greater than or equal to mod a, because mod b is greater than 1, b is not equal to 0, and therefore absolute value of non-zero integer is always equal to 1 or greater than 1. Since b not equal to 0, therefore mod b is greater than or equal to 1, and we have divided this value by this greater than or equal number greater than or equal to 1, and therefore it becomes see bigger. This product is bigger than mod of a, or what is mod of a? That is d of a, and that means d of ab is greater than or equal to d of a. This is d of a, or this is same as the first, or d of a is less than or equal to d of ab. And second is, now it is a ring of integers, and that is I is set of integers, therefore by division algorithm let ab belongs to I and b not equal to 0 by division algorithm. There exist integers q and r, quotient and remainder, belongs to I such that d of that is a is equal to qb plus r, where r is equal to 0 or r is less than b, and this means that is where r is equal to 0 or what is r less than b, that means absolute value of r is less than absolute value of b, or this means that is where r is equal to 0 or d of r is less than d of b, because by definition we have d of a is equal to absolute value of a, and this absolute value of r is d of r. So this satisfies the second condition, and thus for ring of integers with the d value defined as absolute value satisfies both these conditions, first and second, and therefore the ring of integers is a Euclidean ring. So this is first example of Euclidean ring. Ring of integers is a Euclidean ring. Now second can be considered as every field is a Euclidean ring. And for this we shall verify this. So this is easy. What we need is a d function. D of a we have to define for non-negative integer as a non-negative integer, and for every non-zero element in the ring. Let f be field, and we define for every non-zero, I shall write like this, every non-zero, a not equal to 0 and a belongs to f together. We define d value d value of A is equal to fixed value, that is 0. See, it is non-negative. D of A, 0 is non-negative, and therefore we can take d value as a 0, and this is for every element in the field, non-zero element in the field, and that if B is non-zero, belongs to F, then d of B is also 0. So this d function satisfies both the properties, first and second. It is easy to verify. So then what is the first property? You see, AB both not 0 in ring. Here it is filled. So let AB belongs to F, A not equal to 0, B not equal to 0, then AB is also not equal to 0, and therefore what is the d value of AB? AB not equal to 0, AB belongs to F by closure property, and therefore what is d value of AB? This is equal to 0 by definition. So we have defined d value of every element is 0, non-zero element is 0, and d of AB is equal to 0, and which can be written as d of A, and thus here, because d of A is 0, and thus the first condition satisfies. D of A is either equal to d of AB or less than. Here it is equal, and that therefore d of A is less than or equal to d of AB is satisfied. Now what about the second? See, for this AB in the field, we have to consider, let AB belongs to field F and B is not equal to 0. Because B is not equal to 0, B inverse exists. Because it is a field, every non-zero element has multiplicative inverse. Therefore, B inverse belongs to F. And we can now write A is equal to, we will write this as A B inverse into A. So into B we should write AB inverse into B plus 0. We can write A as, because B inverse into B is identity 1 of the field, and then it is A plus 0 which is equal to A, and thus here, that is, we can write this as QB plus R, where what is Q? Q is AB inverse, and this belongs to F, and what is R? R is 0, belongs to F, and thus this satisfies the second condition. R is either 0 or d value of R is less than d value of B. Here R is 0, this is 0, and what is Q? Q is, see this value, Q is AB inverse, it is in the field, and thus every field is Euclidean ring. So that is verified. Therefore, F is Euclidean ring. Now we shall define principal ideal. And principal ideal ring we shall define, and then we shall see the relation between Euclidean ring and principal ideal ring. So definition for principal ideal: an ideal A of a ring R is said to be principal ideal if every element of A is some multiple of an element, if, or we can say it is principal ideal if A is generated by an element A belongs to R, or A belongs to A itself, and that means A is equal to A. This is the notation for A generated by A, and that is AR. R belongs to R. So every element of the ideal is some multiple of A for a fixed element in A. then that ideal is known as principal ideal. We have seen an example of earlier. If I is the ring of integer, then an ideal generated by every integer is principal ideal of a ring of integers. That means if we consider A is generated by say 3, then all multiples of 3, that can be written as multiples of 3. This is principal ideal because every element is of this A is a multiple of 3. Similarly, multiple of 2 generated by 2, etc. are all principal ideals. Now we define what is a principal ideal ring. See, let R be a ring. Then R is said to be principal ideal ring. Principal ideal ring. If every ideal A of R is of the type A generated by A, or that means AR, R belongs to R, or A belongs to R again. So that means if every ideal of the ring is a principal ideal, then the ring is said to be principal ideal ring. The same definition we have considered here. See, if ideal is principal ideal if it is generated by a single element, that may be in A, or if it is in A, then it is also in R, and thus R is ring, then R is principal ideal ring if every ideal A of R is of the type generated by A. A is generated by A, or every element of the ideal is some multiple of a fixed element, that is A, and then the ring is said to be principal ideal ring. Now we shall establish relation between what is principal ideal ring and Euclidean ring as a theorem. And the theorem states that every Euclidean ring is a principal ideal ring. Or if R is a Euclidean ring, then there exists, it is a principal ideal ring means every ideal in that ring must be of this form. If R is a Euclidean ring and A is an ideal of R, then there exists A naught belongs to A such that A is generated by A naught, or that means it is A naught X, X belongs to R. Instead of R we have denoted here as X. It is A, instead of A here we have A naught. So this is the meaning. If R is Euclidean ring, then A and A is an ideal of R, then there exists A naught belongs to A such that A is generated by A naught. So then for every ideal of A of R, this happens, and now we shall prove it. So we know the ideal of a ring are proper ideals are 0 and the ring itself. And now see the proof for this theorem. If the ideal, if A is 0 ideal or null ideal, then we take A0 is equal to 0. And if we take A0 is equal to 0, then A will be generated by 0, all multiples of 0 will be 0, and thus the theorem holds. And the theorem holds in this case, so it is easy. And therefore we assume A is not equal to 0 ideal or null ideal. And if A is not equal to 0, there exists a non-zero element in A. Let A, or there is an element A not equal to 0 and A belongs to A. This exists. Now because it is say principle, we have considered it is Euclidean ring. So there exists d value of each non-zero element, and we choose A0 belongs to A0 not equal to 0, such that d value of A0 is the minimal, means minimum. And this is possible because d value is non-negative. See, this is possible because d of A0 or d of A is non-negative. For every A belongs to A. Here by definition it is non-negative, d of A is non-negative, and from a set of non-negative values we can select its smallest. So therefore we have selected A0. There are many non-negative non-zero elements in A, say A, A1, A2, etc. And these are all elements belonging to A non-zero elements, and they have certain d value, d of A, d of A1, d of A0. We select that value such that d of A0 is the smallest value, and this is this can be done by well ordering principle. We can arrange it in descending order or ascending order and then pick up the smallest. So this is possible. Now we have two elements, A and A0, both not 0 in A. So for A0 belongs to A, both non-zero. A is not 0, A0 is not 0. And there exists a C by the second property, by property of Euclidean ring. See, particular second property, by property of Euclidean ring. See, there exist Q and R, integers Q R belongs to R, such that Q and R both belongs to R, such that A is equal to Q A0 plus R. See here, instead of AB we have considered A and A0. For any AB in R and B is not equal to 0, here we have taken both non-zero, and A is equal to Q into A0 plus R, where what we have, R is equal to 0 or D value of R is less than D value of A0, where R is equal to 0 or D value of R is less than d value of b. B is our a naught, and we shall suppose this statement as 1. Now you see, there are two possibilities, either r is equal to 0 or d of r is less than d of a naught. Now we have q is in r, q is in r, and a naught is in a. We have q belongs to r, a naught belongs to a, and a is an ideal. By the property of ideal or definition of ideal, their product must be in ideal. Therefore, q into a naught belongs to a. And again, a is in a and q into a naught is in a. Therefore, their difference also belongs to a. And therefore, a minus q into a naught belongs to a. But by 1, what is a minus q into a naught? A minus q into a naught, which is r. A minus, take this on element on left side, a minus q into a naught is r, and this is r, and because this belongs to a, it states r belongs to a. Now see, if r is not equal to 0, then what will happen? There are two possibilities for r, either r is equal to 0 or d of r is less than d of a naught. Now if r is not equal to 0, then we have one of them must be true, that is either r is 0 or d of r. See, if it is not possible, then this must hold. Then d of r is less than d of a naught. And see, but this d of r, what we have selected, d of a naught is the minimal value. Here we have selected that value, and this is possible because d of a is non-negative. But this is a contradiction. This is a contradiction contradiction to the minimal value of a dA naught. Or contradiction to our choice as minimal value of dA naught. To our choice of dA naught as the minimal value or minimum or smallest value, because here what we are obtaining, d of r is smaller than d of a naught, and that is a contradiction because this is the smallest, and there cannot exist r belongs to a whose d value is less than d of a naught, and thus we must have, this is not possible, and therefore what is possible, r is equal to 0. Therefore we must have r is equal to 0. And again, if r becomes 0, then what about this equation? Then from 1, a is equal to q into a naught, and that means every element of a is multiple of a naught. Thus, what is a is an element in ideal A. Thus, every element A belongs to A, which is not equal to 0, is a multiple of a naught. A is multiple of a naught, q multiple of a naught, and that means A is generated by a naught. Every element of A is of this type, or that is a naught into some x. X belongs to R, and thus R is A is principal ideal, and therefore R becomes principal ideal ring. Every ideal in R is generated by some element in R. Thus R is a principal ideal ring. And thus what we have proved is every Euclidean ideal is a principal ideal. And one simple corollary to this result or this theorem is a Euclidean ring possesses unit element. And the proof follows from the theorem. Let R be Euclidean ring, then it is principal ideal ring. Let R be a Euclidean ring. Just we have proved every Euclidean ring is principal ideal ring. Then R will be generated by some element. Then R is an ideal of itself. R is an ideal, proper ideal. And R is ideal of R. And therefore that R is generated by some element. We may say U naught. Therefore there exists U naught belongs to R such that instead of A naught we are now changing notation, and U naught we will write. R is generated by U naught, or that means U naught x belongs to R. Now U naught is an element in R. Therefore U naught we can write it is multiple of U naught, and we may write this as U naught into C for some C belongs to R. Now what we shall consider is let A belongs to R. Then A is equal to x into U naught for some x belongs to R. Every element of R is multiple of U naught. U naught is an element in R, so we can write U naught is equal to U naught into C for some C belongs to R. A is an element in R, we can write A is some multiple of U naught. Now what is AC? AC will be C. Here what is A is x U naught, and what we can write this as x U naught into C. AC. A is we have taken as x U naught, and now this can be written as x U naught. See, we will have what is U naught C. U naught C is again U naught C is U naught. So this we can, by associative property we can write x U naught C, and this is x U naught again, and but what is x U naught? That is A. C. Thus what we have is AC is equal to A, and therefore AC is equal to A. Similarly, because it is commutative, we have CA is equal to A, and this shows that C is unit element. C is the unit element of R, and thus every Euclidean ring possesses unit element. So this we have proved using the theorem that every Euclidean ring is a principal ideal ring generated by some element. So thus we have studied definition of Euclidean ring, some examples, and some properties or theorems on Euclidean ring that we have studied. The remaining part we will continue in our next lecture. Thank you for watching the lecture.